It is a pleasure to have today Alex Frenkel, who will tell us about entanglement edge modes from matrix quantum mechanics. Please.
I'm very grateful for the hospitality of Chicago and the Enrico Fermi Institute and the opportunity to talk. Today I'll be talking about a research program that I've been pursuing along with my PhD advisor, Shanae Hartnell, who is now at Cambridge, and also some upcoming work that I hope to post in the near future. And the topic is entanglement edge modes from matrix quantum mechanics, and I'll explain what that is. And this is the outline of the talk. So I'll spend some time talking about why matrix entanglement is an interesting thing to consider. I'll explain how we think about matrix partitions of systems that don't have a base space which we usually partition when we consider entanglement. The story of non-local observables and Gauss law entanglement, which is familiar from gauge field theories and other similar theories with non-local observables. And I will spend most of my time talking about a very concrete example of how to apply this technology, entanglement entropy on the fuzzy sphere, which is a particular state of some bound D0 branes in a particular matrix quantum mechanics system, although the technology is much more general and its applications are much more general. All right, so first, why matrix entanglements? The starting points I typically like to choose is 1993 with by Srednicki, although these ideas are much older, where Srednicki suggests that black hole entanglement is naturally interpreted as the area law divergent piece of some bulk quantum fields. And what does this mean? You take your quantum field theory, you regularize it in your favorite manner, like suppose some oscillators connected by springs, and then you partition it along some entanglement cuts. And if you calculate the entanglement entropy, you find an area law divergent piece. And the intuition is that somehow we should interpret this area law divergent piece as the explanation for why black hole entropy scales with the surface area of a black hole. Shortly after, there was a follow-up paper by Susskind and Oglum, which considered some more general cases of this phenomenon. They considered thermal Rindler spacetimes in quantum field theory, semi-classical gravity, and in particular, and in the bulk of string theory. And what they did was they considered the partition function of quantum gravity on some background Euclidean spacetimes with a conical deficit angle beta. And we extract the entropy of such a system by differentiating with respect to beta in the appropriate manner, and this should give us something like the entropy. And what they conjectured was that the area law divergent piece of the bulk quantum field propagating on the space-time renormalizes the classical bits of the contribution to the entropy that you find from where the Einstein-Hilbert term of the bulk effective action hits the conical deficit. And so really the leading term of the entanglement entropy for a black hole should be thought of as A over 4 times the renormalized Newton's constant plus subleading corrections. And they also perform a calculation of this in bosonic string theory, where finding F for geometries with non-zero conical deficit angle beta requires finding the string partition function in off-shell spacetimes. What they do is they reference a prescription by Zeitlin, which involves either regulating the world sheets and a prescription to obtain the bulk effective action from the sphere partition function by differentiating with respect to log of the UV cutoff. And there's a recent review and extension of this by Alain and Wall. But the point is that this is a prescription for recovering the bulk effective action of gravity from the string partition function, and so the calculation just reduces again to the case of semi-classical quantum gravity. And again, you find this A over 4G Newton. So the dominant contribution that they find comes from sphere diagrams that intersect the conical deficit angle, where the black hole horizon is. And this is the only place where the geometry is off shell. So this is the only place where the sphere partition function contributes. This data is Euclidean time. And what they suggest, the cartoon that they draw, is that once we have a Euclidean time to understand the microstates on one side of the black hole, you should cut this diagram open along Euclidean time to find a picture that looks like some sort of states. And if you do this, you find this sort of cartoon where you are left with some open strings that are anchored to the point where the conical deficit angle pierced through the sphere. And the original full string theory on the entire space-time was a closed string theory. And the expression that you write is that you interpret the closed string Hilbert space as the closed string physical Hilbert space is a subset of an open string theory on one side, where all the open strings are constrained to be anchored to the entanglement cuts, and an open string theory on the other side, where it's a subset and not an equality, because you have an overall non-local constraint that the strings kind of have to match up and form closed strings on the entire geometry. And this is a proposal for how we should think of black hole microstates in string theory. Perhaps something like this could be made precise if we had a non-perturbative definition of string theory where we had control over the bulk microstates on the entire geometry, and in particular in the exterior of the black.
And that doesn't, it's hard to make sense of, right? Because the string world sheet is just passing back and forth through the horizon willy-nilly. And as you try to take the world sheet cutoff away, the oscillations due to the UV divergences of the world sheet become arbitrarily crazy. So the picture isn't some nice string which is looping outside the horizon and coming back to it. It's more a string that is piercing the horizon an infinite number of times, even for a single closed string.
I totally completely agree. Where this is not that there's a lot of difficulties, both conceptual and technical, with making this sort of cartoon precise. I will explain one potential approach to this, not from the string theory side, but from some matrix quantum mechanics side, where we have more control over what it means for, or what the degrees of freedom are. Yeah.
Yeah, I mean, what you're describing sounds morally a lot like trying to factorize the Hilbert space of a QFT across the horizon, which of course you can't do. But so I'm hoping this, or is this a cartoon that it's actually a literal factor Hilbert space? And is it this? I'm basically, I think I'm repeating.
No, this is just a cartoon. This is a cartoon that Susskind and Entanglement draw that perhaps we can try to make precise in a theory where, or in an actual like UV non-perturbative definition of string theory. This is just the motivation. This is just some physical intuition that's the starting point and the motivation. Let me also go into the other side of the motivation. From a holographic perspective, we have come to understand that there is an intimate relationship between entanglement and geometry. So the Kanagi formula, then work by Kibeni, Angomani and Takanagi, Angohard Wall, where and some conjectures by Van Ramsonk and Susskind and Maldacena that we should somehow think of the entanglement structure of the boundary CFT as building up the bulk geometry. And one very concrete example of this is the bulk geometry of two thermally entangled CFTs. So somehow we have, so these are the relevant cartoons with some RT surfaces and the relevant bits of the geometry that are reconstructed by sets of the boundary. And there's also this other perspective where, where the best candidate for a non-perturbative definition of string theory that we have at the moment is some large N theories, be they some matrix quantum mechanics like BFSS or Super Yang-Mills being one of the most concrete ones, where string world sheets emerge from the Feynman diagrams of strongly interacting large N matrices. Right, so the typical Lagrangians that we like to think about are some dimensionally reduced super Yang-Mills that leave us with a commutator squared interaction term that's important for reproducing the string tension. And in the appropriate limits, the partition function or the matrix quantum mechanics free energy, or the partition function becomes a generating function for the partition functions of world sheet topologies. So something like this, where each string is weighted by the appropriate minus chi here by the appropriate characteristic. Right. And an important feature that I want to emphasize about the accepted limit is that adjoint degrees of freedom give rise to finite diagrams of closed topologies, so spheres, tora, etc. And when you insert fundamental degrees of freedom into your Lagrangian, then they can source endpoints of open strings, which is going to be an important feature of what I'm about to talk about. So what are the goals and what are the general goals of this program that we're trying to implement? Does the matrix quantum mechanics know how to stitch together open strings and go to the entanglement cut into a consistent on-shell closed string theory on a connected geometry? So some sort of realization of ER equals EPR. So does the matrix quantum mechanics side derive the picture that black hole microstates consist of open string endpoints, as Susskind and Uglum suggested? And relatedly, does the MKM side know how to reproduce their hierarchy black hole entropy and energy and entropy, a la some matrix black hole states, and introduced by Banks, Fischler, Pablo, and Susskind? And in particular, is there an understanding of bulk systems in BFSS where there is no sort of boundary sphere that we can partition and get a nice Ruteka 90 surface? And the intuition is that sub ADS length scale subregions in the bulk of ADS CFT should somehow emerge not from the CFT structure, but the large central charge structure, the large number of matrix degrees of freedom that are strongly interacting on the boundary. So roughly making precise this intuition that one matrix worth of degrees of freedom on the boundary of super Yang-Mills ADS5 is equivalent to one ADS size region. And this kind of encapsulates the way I'd like to think about this, where you start from n equals 4 super Yang-Mills, which is a CFT and a large N theory. One way you could go is to consider subregions and their entanglement structure and find geometry from entanglements. The other way you could go is to the Entanglement limit and understand geometry as emerging from the on-shell limits of whatever mysterious world sheet theory is emerging on these Feynman diagrams. And hopefully there's some way to connect these two pictures into a consistent description of how geometry is emergent on the sub-ADS length scale, in the S5 directions of ADS5 cross S5, and perhaps the interior of small black holes, and similar puzzles that we have yet to understand. Right. So this is the motivation. I'll, if you have any questions about anything, please interrupt at any time. But, I'll go on to how we think about. Okay. So the systems that we want to consider are some collection of brains interacting with strings, and the intuition is that matrix eigenvalues correspond to the positions of some D0 brains. If you diagonalize the ith matrix, this corresponds to how the brains are distributed along the ith dimension. And if you have a system like BFSS, which only has matrices on a 0+1 background, what do you do when you don't have a base space to partition? And the answer is the most direct thing to consider is something like this, where you have an n by n matrix and you chop it up into blocks. This is one of the most natural ways to think about subsystems of these brains. So we have 4 blocks that a matrix gets chopped into. The sigma blocks, the sigma block corresponds to all, if I take some subregion of the geometry in which the brains are propagating, all the brains and the stringy interactions of the brains within a subregion. The sigma bar, everything in sigma bar, which is the complement of my subregion sigma, and the off-diagonal blocks will be the ones important to our story. And these are the strings that cross between the two subregions that are going to cross the entanglement cut, and these are the degrees of freedom whose structure we're going to be trying to understand. And because these strings are degrees of freedom, which are crossing the entanglement cuts, they are intimately related to the problem of non-local observables and how we treat non-local observables and non-local constraints in our Hilbert space when we try to partition the Hilbert space. So in particular, they're similar to Wilson loops and gauge theories. And again, in string theory, there's a reason to believe that they dominate the geometric contribution to the entropy. So it's like what we try to understand from the matrix perspective. And the point is going to be that both cases are treated the same way. We extend the Hilbert space to allow strings whose endpoints are anchored to the entanglement cuts. So we start with a closed string theory, which we have a closed string theory because in these matrix models, we only have adjoint degrees of freedom. So in the SF limit, we only get closed string diagrams. And we want to understand where the open strings come from. And there's quite a bit of references. These are the ones that I in particular found most useful for how we think of extending the Hilbert space and thinking of the physical Hilbert space of a subsystem of an extended Hilbert space that has a factorizing structure.
Is that well defined? I mean, can you extend it in multiple ways? It sounds like you are kind of gunning for a known answer when you're saying you're going to do that. Like,
Sorry,
how do you know what additional degrees of freedom to add? You say you added some unphysical states. How does the answer depend that you're going to get depend on the choices that you make there?
so there is, in principle, many ways to do this. If you're doing things correctly, or there should be some universal area law behavior that is independent of your choice of regularization of the theory.
This is just a regularization.
It's not. It usually involves regularization. So I think about how best to answer this.
It sounds more like a choice of boundary condition, something like that.
It is a choice of boundary conditions, and when you're working with QFTs, yeah. So the regularization is an independent thing that you have to include in order to make the finites entropy precise. I agree this stems from a choice of boundary condition, and a lot of the work in particular, Donnelly and Friedel is showing that there are typically natural choices of boundary conditions that corresponds to the remnants of some UV degrees of freedom that you've integrated out.
What's that in this problem?
I'll get there.
In any system that's going to have some non-trivial spatial extent, you're going to have this issue, the same issue we've been asking about all along, which is that sort of every momentum mode of every non-abelian field is going to have this partition that you're making into blocks, and then if you're trying to partition space, then you're going to have some structure where all the way up to the UV, you've got some matrix degrees of freedom where the physical things are only single traces because you have to apply the Gauss law constraint. But now you have to keep track of all the non-abelian structure where, well, like in your picture, right? You have some eigenvalues that are over here and some eigenvalues that are over here, and you want to treat now the not off diagonal degrees of freedom that connect those two sets of eigenvalues. And you're going to have to keep track of that up to arbitrarily high frequency and spatial momentum in gauge theory. It just sounds like a total mess. But if you're going to treat single matrix quantum mechanics, then it's particularly clean because there's like one matrix. It has one set of off diagonal blocks, and we can just add them to the Hilbert space. and their
But that sounds like a simple, nice thing to do, but I'm sure you could come up with more convoluted additional degrees of freedom to add. And
yeah, well, this one is motivated by having one
yeah,
underlying matrix that it contains both blocks.
yeah, no, I get it, but I guess what I'm trying to say is that there seems to be some choices here. And about kind of how you extend this Hilbert space, what additional degrees of freedom you add. And it's not clear to me that the answer is independent of those choices.
I agree that in principle, the answer is not independent of these choices. The choice that we're going to make here is very much inspired by this interpretation of how the degrees of freedom are associated to where the brains are in the target space of the brain world volume. Hopefully I'll convince you that the structure of these off-diagonal terms is robust enough to how precisely you choose to decompose the degrees of freedom.
But what does that mean? Does it mean, I mean, could I destroy the whole calculation by choosing different kind of off-diagonal degrees of freedom? What does it actually mean that it's robust? Like more quantitatively?
That let me go through the choice that we make here, and then I'm happy to discuss this after in reference to the choices of decompositions that we make.
Maybe one thing to be said is that if this is coming from some field theory with well-defined UV fixed point, then the sort of regularity structure of the vacuum wave function is going to highly constrain. It's like everything has to have some kind of universal behavior asymptotically in short distances, and that's going to highly constrain what you can do.
I don't understand this picture, so it's a much lower level. Didn't understand this whole discussion, but just the notation.
Okay.
These points are points in F, which is called here X space, yes?
And
there are points, black points on this picture.
yeah, so
there are points in what you call X space.
yes, so let's say I have 9 matrices.
No, don't worry about the points in some X space.
Yeah.
Sigma and sigma bar are some regions along the matrix. What is sigma exactly?
Yeah, so let me try here.
Just one X. There's no index I. So there's one X, and this capital X is an n by n matrix, yes?
Yeah.
Okay, so sigma is some region along in the matrix.
Yeah. Let me give my answer. So if I think of brains as physical objects propagating in space, then I draw an entanglement cut in that space.
That space is X space, yes.
This space is the eigenvalue space of one of the matrices, for example.
So there are n eigenvalues, yes?
Yeah, there's an eigenvalue, so there's
the space you drew is a space in the matrix, not in the space of X's. I guess I don't understand the picture. Usually when you say we have a brain, and on the brain there's some field capital X, that means the brain is localized in X, and we can move the brain by changing X. This is not the picture you draw on the board. Yes.
This is the picture.
So the board is X space?
Yes, the board is the eigenvalue space of xi.
Okay, so you now said two opposite things. One is a brain. Each brain could be a point in some space labeled by some x's.
Yes.
So, for example, the board you drew it on is 2-dimensional.
Yeah.
It could be an x1 and an x2.
Yeah.
And each brain is a point on the board.
Yes.
It has some x1 and some x2. And that line you drew is a line in X space. That's what is drawn there. But now the other thing you said that the points, the 2 points on the left and the 3 points on the right, they are just different eigenvalues of the matrix.
So how I'm partitioning up my
contradictory things. I just don't understand.
How I'm partitioning my degrees of freedom. Maybe it's a bit of a language of speaking, but how I'm partitioning out my system is I'm taking the matrix, say x1, say this is the x1 direction, this is the x2 direction. I'm considering the eigenvalues of this matrix.
Okay.
The eigenvalues of this matrix will have some distribution. And I'm keeping only the eigenvalues. So the spectrum of this is some collection of n eigenvalues of xi. And I'm keeping in my subregion only the eigenvalues that satisfy xi, little xi, is less than or equal to, say, 0. If this is at x1 equals 0. Sorry.
So sigma is the subset of the eigenvalues that are to the right of that line?
Yeah, or to the left here, yeah.
On one side of the line.
Yes.
So sigma is the region in the matrix, then, right?
Yeah, so
It's not a region in X space. Like the line is a line in X space, but sigma is a region along the matrix.
yeah, so the way that we connect the two is we introduce a projection matrix to define the subspace of the matrix, and this projection matrix is a function of, say, x1. So you can connect the two descriptions in this way by introducing a projection matrix that's a function of the matrices. I'll have those equations on the slides in a bit.
But these X's are the dynamical fields, right? So
Yeah.
different, you're summing over all the configurations.
Yeah.
So this sigma is fluctuating like crazy. It has nothing to do with what we call the entanglement surface.
So if we fix M, if we just fix one collection of the branes, then yes, I agree the sigma is fluctuating like crazy.
How do you fix M? The definitions you just gave, M fluctuates like crazy, right? Because
You mean that the number of branes in the subregion fluctuates like crazy?
yeah.
Yeah, I agree.
So what do you mean by fix M? That's what I don't understand.
No, I'm saying if we were doing something different. I misunderstood the question. Yeah, but yeah, I agree that the number of branes in the subregion is fluctuating like crazy, and we allow for all possible brane numbers in the subregion.
Okay, and what is the question you asked? Maybe you didn't get to it yet.
Yeah, no, so the question will be calculating the entanglement between the states of the branes on one side of this cut and the states of the branes on the other side of this cut. But hopefully the upcoming slides will make this clear. Right. Yeah. So I'll make this precise. Okay. Maybe I should go on. Right. So. Yeah. So this is another cartoon of what we want to do. Yeah. So okay, I should have just gone to the slide. So sigma is some subregion and some space, and we have some strings that are crossing it from sigma to sigma bar. And we want to find the matrix language description of what it means to do this, to take the string that's crossing the cut and break it up. And the important objects in this consideration are going to be the generators of the UN adjoint symmetry in the matrix quantum mechanics. So xi commutator pi I summed over I is the generator of the global UN gauge symmetry. And we can consider the sigma subblock. So we can also partition this matrix of generators into some blocks of sigma. And we can just by matrix multiplication, rewrite it in this way. So this commutator, the subblock of this commutator is going to consist of a bit built out of just the matrices that correspond to the degrees of freedom interior to a subregion. And we're going to have another bit which corresponds to the off-diagonal matrix blocks. And the ground state satisfies this expression. It's annihilated by all n squared generators of the global UN symmetry, but it is not going to be annihilated by the generators of the subgroup of UN that corresponds to the matrix degrees of freedom in the subregion. So all the global generators annihilates any physical state psi, but this corresponds to relationships where G psi is equal to minus Q psi for this sub. And when we integrate out the degrees of freedom outside of sigma, so we integrate out, say, 3 of the blocks, we are generically left with a density matrix in a non-trivial representation of Right, and when we have a state that's in a non-trivial representation of it's no longer true that these degrees of freedom are just going to generate closed topology Feynman diagrams. The degrees of freedom in the subregion are in general going to have open diagrams in their pictures. So this is the relationship that I want to draw. So the full wave function of the matrix quantum mechanics generates closed strings, and these off-diagonal blocks are bifundamentals under the cross minus m subgroup that just keeps the bit of the gauge symmetry that's internal to these 2 blocks. And when we have bifundamental degrees of freedom that are fundamental from the perspective of one of the subregions, they're going to allow open strings to be generated. So this is the perspective that we're going to take about how to find these open strings in the matrix, in the subregion of the bulk geometry of the matrix theory.
So M is fixed or not? I don't.
M is not fixed. So
then what? So I don't understand. Yeah. So the N as in Nancy is fixed in the whole calculation.
N as in Nancy is fixed.
So
yes.
now you want to split it into capital M and capital N minus M, and you need to write some stuff to get something about the capital M, the system with the capital M. Yes.
Yes.
You did understand it correctly.
Yes. So
the capital M is now not fixed.
Capital M is not fixed. Let me explain it in this way. So let's say I define a function theta of x1 that is equal to just the Heaviside theta function, so a step function of the matrix x1. So I can evaluate this function by diagonalizing x1, then just keeping the eigenvalues that are less than 0, then rediagonalizing it. So in the basis where x1 is diagonal, so if for diagonal x1, then theta of x1 is going to equal to some 1s along the diagonal and some 0s along the diagonal. And I have an observable that I can build out of my x1s. That's a single trace observable. That's trace of theta of x1. And this trace of theta, this trace of this projection matrix, counts the total number of branes that are inside my subregion.
But in this O, an input into this O is M, yes? How many ones there are?
The input into this, which O?
Well, you wrote in the equation where your finger is O of x1 equals to this matrix.
Yeah.
On the right hand side, the equal sign.
Yeah.
That matrix has capital M ones and capital N minus M0.
Yeah, but the point is that the M will have a non-zero variance. So the expectation value of trace of theta squared minus the expectation value of trace of theta of x1 quantity squared is going to be non-zero. That's just a statement that, so let's say I forget that I'm dealing with branes, and I just have some free fermions or some free particles propagating in a one-dimensional geometry. If I draw an entanglement cut in that geometry, then the total number of particles on one side is going to fluctuate. But I can still evaluate an entanglement between the particles on one side of my entanglement cut and the particles on the other side of my entanglement.
So basically, you're saying the matrix has some wave function.
Yeah.
Nobody can stop me from integrating out the 3 blocks other than the upper left block.
Yeah.
I get some wave function for the upper left block. While there's a Gauss law constraint that says that the whole wave function is in a singlet state, the upper left block is in some state with non-trivial representations. And it's because I integrated a bunch of stuff out from a pure state, I get some kind of a mixed state. which is a superposition of states of blocks of different sizes, upper left blocks of different sizes.
Yes.
And in different representations.
Precisely, yes.
So all M's are allowed, they're just different components of a wave function, which is in a mixed state, because you integrated a bunch of stuff out.
And I think you can also phrase it as different, you can phrase it in the language of different super selection sectors for the subregion. Yeah, which are labeled by M and the total representation. Okay, so let's make what Emil said more precise. So the full state commutes with all the generators of the full UN group. And upon tracing out the 3 of the blocks, then we have this expression instead where rho of the subblock commutes with G sigma plus Q sigma. And I've denoted this double commutator with the Q symbol in brackets to denote that it's a commutator on the Hilbert space and not a commutator of the classical matrices. And the Q sigma blocks are entirely built out of these, the Q sigma is entirely built out of the off-diagonal blocks. The Hilbert, and so they only act on the Hilbert space corresponding to the sigma sigma bar degrees of freedom. So they'll act as C numbers on the sigma sigma degrees of freedom. And this implies that, so we get commutation with Q sigma for free, and this implies that rho sigma sigma must compute with G sigma. Just the X sigma sigma comma pi sigma sigma commutator on the, just built out of the upper left diagonal block degrees of freedom. And schematically, due to Schur's lemma, the reduced density matrix will decompose into a direct sum over all possible representations of UN of reduced density matrices on the sigma sigma degrees of freedom. And this direct sum will also, it'll be labeled by a direct sum over R and a direct sum over M. But I'm suppressing the direct sum over M for notational convenience.
So
Yeah.
it looks a little bit weird to me that you're integrating out things which are not heavy necessarily. I mean, I guess there's a difference between matrix quantum mechanics and a high dimensional field theory where you could pick a vacuum and say the n minus m degrees of freedom that you want to get rid of here are heavy by moving them far away, say.
I don't care about things that are heavy or not. So I'm not integrating things out in order to get an effective field theory for the light degrees of freedom. I'm integrating things out because that's how I get a reduced density matrix on a subsystem that I can then evaluate the von Neumann entropy.
We should somehow run into the same problem of trying to integrate out things in the masses in terms of bad infrared behavior. I'm not sure why you get multiplying quantities.
Sorry, if I just have some sort of like massless free fields in any dimension, I can still ask about the entanglement structure of the vacuum, even though I have many light degrees of freedom that I'll be integrating out on one side.
Yes. There you do it in terms of space, but here you're doing it in field space.
Yeah, but so the whole point here is that, so basically the extended Hilbert space that I'm considering is just the ungauged theory. So because this is just, so I can think of the matrix quantum mechanics not as a theory with a UN gauge symmetry, but as a theory with a global UN symmetry, whose Hilbert space decomposes into a direct sum of Hilbert spaces over the different representations. And in that language, each of these blocks are just independent degrees of freedom. And because this is a finite, because this is a quantum mechanics problem with a finite number of degrees of freedom, there's not any subtlety in what it means to integrate out some subset of the degrees of freedom. What I mean is that my Hilbert space directly decomposes into a product of H sigma sigma, tensor H sigma sigma bar, tensor H sigma bar sigma bar.
I think the question that Sav is asking is if the X sigma sigma bar degrees of freedom are not in some sense heavy, then the what you get by trying to integrate them out is something that's non-local in time. Because if those degrees of freedom aren't in some kind of like oscillator ground state where they're frozen and their wave function is pinned to what the degrees of freedom you're leaving behind are doing, then they just sit there and they fluctuate over long time scales, and the attempt to integrate them out leads to something that's non-local. Anytime you try to integrate something out that's light, the problem you run into is that there are correlations over time and space scales which are longer than the cutoff you try to impose on the system.
Sorry, maybe I can clear things up. I think I've accidentally slipped into the wrong language. I should say tracing out these degrees of freedom. So I'm entirely thinking from a Hilbert space perspective, where if I have a reduced density matrix on the full Hilbert space, I'm always free to trace out sigma, sigma bar, and the sigma, sigma bar factors of the Hilbert space. This is always a well-defined thing to do. And you can ask whether or not I get, so this is going to be my reduced density matrix on the sigma, sigma Hilbert space. And you can ask whether or not I'm going to get anything sensible and local in the structure of this guy. But whether or not I do, this is always I don't see any conceptual subtleties with.
Well, I think it's fine as a finite dimensional matrix.
Yeah.
But the question is, if it was not a finite dimensional matrix, if there was something gapless, is the right-hand side IR safe?
If it's not a finite, I'm always thinking at finite n. So whether or not there's subtleties like this at infinite n, this is a good question, but I'm always thinking at finite n.
You're free to do that, but why won't there be there's going to be some effective dynamics. Why doesn't that effective dynamics how is that effective dynamics local in time?
Yeah, are you gonna evolve this forward in time? Because then you're
No,
gonna-
no. So this reduced density matrix on the full state, it's just some wave function. I in principle don't care about the dynamics of the theory. I'm just asking about what the reduced density matrix at a particular time of the sigma sigma degrees of freedom are.
Mhm.
Again, it's like
Yeah,
if
you
I
can
had
do that
some.
at some fixed time, but for instance, if the system, if there's no real barrier, corresponding to your partition, for instance, there are terms in the Hamiltonian which cause a piece of the wave function with some value of m to evolve into a piece of the wave function with some other value of m, because stuff can freely go in and out of your region. Right? Only if the system dynamically has some energetic barrier for stuff going from one value of x to another value of x.
Yeah.
Whether you say, okay, the dynamics at low energies is confined to x's being in your preferred region, and then breaking the Hilbert space up into these little super selection sectors, the dynamics will stay in that super selection sector, and you can successfully integrate everything out. Otherwise, the dynamics is going to mix all this stuff up like crazy.
I agree, but I agree that dynamics might be very complicated, but that's fine from the perspective of this definition.
If you're going to compute the entanglement entry at some fixed entropy at some fixed time, it's probably okay.
Yeah, that's all I'm interested in doing. I'm interested in the ground state wave function of this theory, and I'm interested in computing the entanglement at some fixed time. And yeah, I'm going to do this I'm not going to do this by some replica trick. I'm going to do this just from working with the wave function. So I don't think that there are any issues here. It's like I have some finite set of coupled oscillators, and you just trace some of them out.
Why are you even saying fixed time? Maybe that's what caused confusion. Like it's just entanglement entropy of the ground state, right? There's no time dependence.
Sorry, that's how I tried to phrase it
Dynamics.
originally, but
Yeah, it's not a dynamic
I'm just saying, I just introduced the word fixed time to emphasize that I don't see where non-locality and time is going to be relevant. That might be relevant in some Euclidean replica trick like path integral, but if I'm working at it from a Hamiltonian perspective, then I don't. This is just a well-defined thing to do.
Okay.
Right. Right. So going on by Schur's lemma, we have this, that on each irreducible representation of UM, the reduced density matrix is maximally mixed. And this is just imposed on us by the global UN symmetry. And if we just take trace over the Hilbert space of rho sigma log rho sigma, the reduced density matrix on the sigma sigma degrees of freedom, then we get a sum over irreducible representations of PR log dim R. And minus sum over R of PR log R. So this is going to be this is typically the dominant term, and this is some Shannon entropy like term for the uncertainty in which representation. And in most cases that we find in gauge theories in general, and in same logical string theory, where there's a little bit of control, is that there's a particular representation that dominates entropically. And so there's particular log dim R that dominates, and that's the log dim R that we're going to try to find. And the way that we're going to do this, oh yeah, so just a couple physics words.
Sorry, why is there a dominant representation?
This is not necessarily true. So in order to show that this is true, you have to show that the uncertainty in log dim R. This is just a statement that this is typically what one finds in the vacuum structure of gauge theories, and that's also what we're going to find here. Yeah.
Sorry,
Yeah.
is rho sigma the same as rho sigma sigma on platform?
Yes, sorry.
Then is the von Neumann entropy of rho sigma the same as von Neumann entropy of rho sigma bar?
Well, yeah, so we have to be careful. So I've chosen a bit of an asymmetric decomposition where sigma bar consists of 3 matrix blocks and rho sigma consists of 1 matrix block. So in a priori, you shouldn't expect that any sort of entanglement measure that we calculate for this block is equal to an entanglement measure that we calculate for this block, but that's going to turn out to be true. Yeah. So I have made a choice for how to partition my UV degrees of freedom, and we should hope that this choice still just computes something about the boundary of the subregion and not something crazy.
But then I think usually the entanglement between the two parts should be a mutual information of the density matrix of the diagonal blocks, instead of just the von Neumann entropy of rho sigma.
I agree with this. I'm happy to discuss this later because I'm running a bit short. I agree with this, but let me show you the quantity that we're going to be calculating. Yeah. Good. Yeah. So just some physics. We think of G sigma as describing the state of Wilson loops anchored to the boundary of sigma, and Q sigma as describing the state of the boundary charges. So like in E and M, this would be you have some flux tube that's anchored to the boundary, and then the endpoints of this flux tube are like some electrons and positrons that are some virtual particles that are popping in and out of existence across the entanglement fence. And quite often the sigma bar sigma degrees of freedom are suppressed when the branes are separated because these correspond to some heavy objects. So it's easier to work with Q sigma just because it turns out that it's going to be some sort of low rank object. And this is just an observation. And in the case where the second Casimir of the dominant representation is large, trace of Q sigma squared is enough to read off what log dim R is to leading order. So that's the quantity that we're going to calculate, trace of Q sigma squared. And we're going to get some representation that's labeled by some Young diagram, and there's going to be some collection of terms with some box lengths. Right. So let me talk about, in the time that I have left, a particular very concrete example that that was the subject of I think with Sean in January, and it's going to be some collection of branes that form a fuzzy sphere. And we're going to consider a block decomposition of the relative matrices, and the cartoon is that the diagonal block corresponds to the degrees of freedom in the subregion, and the off-diagonal block corresponds to some strings that are connecting the interior of the subregion to the interior of the. And we're going to focus on this particular three matrix model, so I runs from 1 to 3, and this potential is a particular square that enforces the sorry, there should be a plus. No, sorry, that's correct. That's correct. Sorry, I checked myself. Right. So this is can be thought of as a truncated version of BMN, where we've forgotten about 6 of the matrices, and we've chosen a potential so that representations of SU2 are the classical minima of this potential. So the strategy is going to be we're going to work around the classical minima. We're going to consider wave functions that are localized to the classical minima when U and N get large, and we're going to expand in some quadratic normal modes of the potential. Yeah, so there's like an M2 brain fuzzy sphere, and right. So these matrices build up a sphere of radius UN. It's going to be read off from the expression that the square coordinates, that's like the sum of the matrices squared, is proportional to the identity. So all the branes are at the same radius. And when we have a system like this, the non-commutative algebra of the fuzzy sphere is built up out of the matrices. So each matrix, each classical minimum matrix Ji is associated to some coordinates along the fuzzy sphere, just because of how we interpret the eigenvalues of the matrix as the position of branes. And commutators of these matrices become derivatives or angular momentum operators, or there are fuzzy analogs on the fuzzy sphere. And one can define a basis of matrix spherical harmonics that satisfy the fuzzy versions of the usual definitions of spherical harmonics on the sphere, where instead of derivatives with respect to phi and theta, we have commutators with the coordinate matrices, which are the non-commutative analogs. I guess one way to get comfortable with the fact that commutators on non-commutative geometries should be derivative is that commutators satisfy the Leibniz rule. Right. The structure of spherical harmonics in as just particular matrices, and the basis where J3 is diagonal is rather simple. You have one diagonal that's occupied. It's the mth diagonal from the center for the YLM spherical harmonic. And the entries of the matrix are literally just a discretized version of the classical spherical harmonic. So this is some collection of matrices that build up the algebra of functions on the fuzzy sphere. And this is what, in general, another picture of what we're going to want to do is just consider some mess of an entanglement cut that can have some non-trivial topology, that can have a bunch of different regions. They can be nested inside each other if you want. And what we're going to want to hope to find is that the structure of the dominant representation is entirely determined by the geometry, i.e. the length, or the perimeter, and the topology, i.e. the number of cuts in the entanglement cut. I'll go a bit quickly and to finish up. So we're going to want to evaluate the commutator of trace of Q sigma squared, and I'll skip some commutations. Theta sigma is the projector onto the subregion. It's precisely the non-commutative analog of the characteristic function of my subregion. That's a function that's 1 inside the subregion, 0 outside. And after some manipulations, we find that the expectation value of trace of Q sigma squared is a sum over the different normal modes weighted by their energies of this square of some commutators of sigma. And again, remembering that commutators are like derivatives, this is like the integral of some second order differential operator of or matrix elements of some differential operator on this fuzzy sphere with respect to of the heaviside functions. Yeah, so maybe the interest of time, I'll skip a lot of the technical steps. But the point is that once you evaluate everything, you find something miraculous emerges, which is that the expectation value of trace of q sigma squared with some prefactors that scale with n. The reason that you get the scaling with n is because this sum ends up being dominated by the highest energy modes because their contribution is proportional to the energy of the lengths of each of the bits of the entanglement cut squared. So these partial sigma k's are just the boundaries of these guys. So the expectation value of the second Casimir is just you take each bit of the entanglement cuts, you evaluate its perimeter, you square it, and you take the sum. So the structure of trace of q sigma squared is precisely determined by the geometry. Right. And in fact, you can make a stronger statement, which is that in the dominant representation of the state of the interior, the way you build up the relevant Young diagram is each row in the diagram is determined by one of the boundaries of the entanglement cut. So if I have like 3 disconnected bits of my cuts, then I'll have 3 rows in my relevant Young diagram, and each row is going to be given by the length of that cut on the fuzzy sphere. And you can directly use this to evaluate. What log dim R is. If Li is much smaller than M, then you get this area law-like behavior or perimeter law-like behavior where you're summing over the length of the entanglement cuts times some logarithmic correction. And when log dim R, when the lengths are much larger, then the number of branes, so when they're densely packed, when they're very sparse, then log dim R is just going to count the number of branes inside the subregion. So it's like a perimeter law versus a volume law in the fuzzy sphere. Right, so let me skip all this to the summary of the things that I want to emphasize. So entanglement computations in MQM provide one approach to an explicit realization of the Susskind-Algom picture of closed strings splitting into open strings directly via the ATEF diagrams. Color partitions provide a hope for understanding subregions and BFSS-like theories because there are no boundary degrees of freedom to separate. And yeah, I skipped C = 1 stuff. Right. And the entanglement is quite generally regularized by the emergent coupling constants, which is here the emergent coupling constant is the emergent coupling constant of the fuzzy ENM that emerges on the surface of the fuzzy sphere. Yeah, sorry for going over time. Let me just stop here and ask if there are any questions.
So getting back to this question of what you're integrating out. So in the particular example you did of the fuzzy sphere,
yeah,
there's a sense in which you're tiling this sphere with D0 branes. There's some. The off-diagonal matrix elements are in some sense masked up by the commutator potential.
Yeah, exactly.
And so there is a sense of integrating out the off-diagonal strings to get a wave function for the eigenvalues, because the eigenvalues are sort of pinned to little regions on the sphere, modulo this overall question of imposing the Gauss law constraint.
Yeah.
So if I didn't have the BMN potential and I just had this straightforward BFSS model truncated to 3 matrices, now the eigenvalues aren't pinned to anywhere, they can fluctuate around. And I would imagine that the dynamics naturally takes me in between, situations where there are 5 eigenvalues in your region and 7 eigenvalues in your region. And so I have to sort of keep track. I say integrating out the off-diagonal degrees of freedom is kind of a bad idea because you sort of have to keep track of the entanglement structure of the wave function. Because sometimes you'll be integrating back in those off-diagonal degrees of freedom. And then once that eigenvalue leaves the region, you have to integrate them back out and so on. So it doesn't seem like this way of partitioning the matrix is kind of a useful thing to do if the eigenvalues aren't sort of pinned to being in the region you're looking at and the other eigenvalues being pinned to being outside of it.
Yeah, so this is a very good point. I was trying to find a slide, which I think I may have accidentally cut out in editing, so the fuzzy sphere does not exist in the N-tuft limits. But what you do find in the N-tuft limits is the master field. So there is an emergent novel classical limit at large N when you take the appropriate limits to let the sphere diagrams dominate. So what I'd like to argue is that instead of working with the classical fuzzy sphere matrices in these expressions, in the commutators of the matrices that you would insert into these commutators would be these quote unquote infinity by infinity classical minimum matrices that in principle you could calculate if you had a supercomputer for BFSS or BMN. So another way of saying this is that both the trace of theta and this second Casimir are single trace observables of the matrix degrees of freedom. So it's reasonable to hope that they should approach some classical limits if you take the N-tuft limits, and the variance in M is actually going to end up quite small or suppressed with powers of 1 over N. So I think there's plenty of room to hope that some similar structure like this could emerge.
I think Ewan was pointing out, not just large N, even at finite N.
Yeah.
The difference between BFSS and this BMN story is a gapless spectrum versus a gap spectrum with a much more complicated vacuum in the BFSS case. And the structure of that vacuum, you can't, I think, circumvent in any simple way. I mean, that was always the problem with BFSS, was understanding aspects of that vacuum.
I agree.
BMN has a very simple vacuum by comparison, right? I mean, it's sort of classical plus small fluctuations, but BMN has a gapless spectrum with a vacuum in which things can separate infinitely far.
Okay, I do agree from this perspective. BFSS is more complicated, but I can still, so definitely we don't have handle on BFSS. Still, this sort of definition of tracing out some of the Hilbert spaces, each of these Hilbert spaces and this tensor product is well defined for BFSS. Or maybe you're arguing that it's not well defined, and I'm not understanding why.
Intuitively, I feel like this should be a major problem with doing this in that setting.
Okay. So I agree that. Okay, so maybe there's some sort of problem that we're not understanding, and then there's a reason why the fuzzy sphere simplifies, and there's something that
for something like 2A black holes or whatever,
Yeah.
I think Juan will tell you that this is good enough. BMN is good enough.
So let me rephrase it then in terms of this trace of Q. So this trace of Q that we're calculating, you can write Q just as a function, just as some long polynomial of the matrices. So this, trace of Q squared, this expectation value is just some really long trace of a string of matrices, or a sum of strings of matrices. And so at finite n, this observable, which is determining the structure of the reduced of the dominant irreducible representation, or at least the expectation value of the second Casimir of the irreducible representations, this I think is a well-defined thing. Because this is not being computed as an expectation value in H sigma sigma. It's being computed as an expectation value on the full Hilbert space.
Email, I don't understand what you're saying. This vacuum you're complaining about in the FSS is just gravitons, as you know. So if you look at flat space-time, you put some line or some surface in space, and you just treat gravitons as field theoretic degrees of freedom. You can do a calculation of them just as you would in Cernicki, right, for a Klein-Gordon field. So what's, I mean, it's going to be UV divergent. Are you complaining that it's UV divergent or what?
No, I'm saying that there's some wave function.
There's
So
no
it's just
technicality, but in the end, we agree that this calculation he's trying to do in that context is the same as asking in the continuum 11-dimensional gravity. The question, you partition space into two parts, and you treat the gravitons as just like envelopes of Klein-Gordon fields, and you calculate the spatial entanglement between the two sides. The matrix BFSS better just reproduce this, right? And the answer is going to be the same as in Cernicki, right? The area over, well, some epsilon, some UV cutoff. I don't know what.
No, let's be careful. So in that case, so we're not talking about having like individual gravitons and saying, where is the graviton? Is the graviton over here or over here?
Yeah.
Right. That's the center of mass of this blob. We're talking about the individual eigenvalues.
We being him.
Him.
Well, no, but his calculation in the end has to agree with what Cernicki would say. Without, like, Cernicki never heard of BFSS and all of this. He would just treat the gravitons as field theoretic degrees of freedom.
Right. So let's suppose we have one graviton. It's got longitudinal momentum n. Okay. And Cernicki would tell you how to calculate properties of that graviton wave function. Right. So that, and those properties are some behavior, basically the center of mass of this thing of size n. He's reaching inside the graviton and decomposing it into subbits.
So you claim that
different longitudinal.
You'll get a different answer from Cernicki. That's what you're saying.
I'm saying I don't understand if I've got a wave function where the eigenvalues the individual eigenvalues wave functions are spread smoothly over two regions, and you try to split it apart into the graviton being over here and the graviton being over here, that it's just a fluctuating mess. It's something where the thing you were complaining about before, that, how do you decide, what M is? M is, it's a sum over all possible partitions into subregions, and then a dynamics as the wave function, as the graviton oscillates, being over here, having different values of M, which are evolving into each other.
So I'm just trying, so your claim succinctly is just that you don't understand how this calculation agrees or disagrees with the Cernicki calculation.
Correct.
That is what you're saying.
Right.
And you could say that's a complicated thing.
It's a complicated thing. And it's complicated because
Cernicki doesn't have to worry about everything you said. Right? The graviton for him also could be on this side of the wall, on that side of the wall. He sums over all of this easily, right?
Even if you look at the graviton vacuum, you get this divergence, but then, I mean, the argument that I think now is made rigorous is that, the running of G Newton cancels the divergence. And I mean, that's a kind of a hand wavy argument, but I think it's morally right. The stuff that Witten's been doing recently. Is that similar to what's happening here, or?
Yeah, so again, all the calculations that I presented here, it's certainly not for BFSS, it's for a much simpler model. And in the model that we're considering, the the relevant quantities are precisely regularized by 1/n.
Mhm.
And powers of one over the emergence coupling of the boundary. So the guess or the hope is that something similar could emerge for BFSS, where if you make this UV partition of the fundamental deep brain degrees of freedom, then you could hope to recover something like an aerial. Maybe it's unreasonable to expect this for the vacuum structure of BFSS, but perhaps for black hole microstates, where we do expect that the entanglement understanding of the black hole entropy should somehow be made precise in the UV, and should precisely be regularized by 1 over the appropriate order 1 factors times 1 over n squared. Oh, sorry, but n squared or 1 over g Newton. There, something like this has perhaps a stronger chance of being the correct way to think about this. But in general, this is maybe I should phrase it as, if we take the interpretation of the eigenvalues of the BFSS matrices as telling you where the brains are located in the emergent space literally, then this is the most direct separation of the degrees of freedom that you could do. And if this doesn't reproduce something like A over 4g Newton, if you were to compute it with the actual BFSS wave function, maybe you have to do something more clever. But at least from the Tufts diagram perspective and from the small coupling perspective, it's not. I'm not sure if that answered Emil's question.
My guess is the opposite, that to get the regularized Srednicki entanglement entropy in the flat space, this may work, but for the black hole, the A over 4g Newton comes from a completely different place. It's the microstates of black holes, and I don't see anything this has to do with that.
Well, if you believe these black holes in BFSS papers, they consider black holes as just thermal.
Okay, well, we're already keeping.
Oh yeah, sorry, yeah. Let me, yeah.
So let's thank Alex again for this talk.
You should stop sharing.
Yeah.